In this example, we've got a collar P, which is constrained to be moving along a smooth rod, with the smooth rod built within a cart as shown. The cart is able to move along the x-axis, along a horizontal plane, and someone has grabbed onto that cart and they're pulling it to the right with an acceleration of a. And what we're asked to find is, what is that acceleration have to be in order that the collar does not slide relative to the rod? Okay, what that's saying is that if A is too small, we know what happens. If A is too small, then the collar, I guess it's called, will slide down. On the other hand, if A is too large, then what will happen is that the collar will slide up the rod. And I think you can envision that if you pulled on the cart too quickly to the right, you would find that that collar would tend to slide up. What we're asked to find is, what A does it take to put it right there in the middle, where A is not so large that it slides up, it's not so small that it slides down, but right there in between. So let's look at the forces. Let's look at the FBD acting on the collar. Okay, so what we have here is a normal force N, no friction force because it's smooth. We've got the weight force there of mg, and that's it. What I'm going to do is define a set of coordinate axes here. X is along the incline, y is perpendicular to that. So whenever I write down Newton's second law, when I sum forces in X, what I mean is I'm summing forces along the rod, and if this angle here, defined as a theta, is there, then the angle between the weight force and the y-axis is also a theta. So the forces acting in X is mg sine theta, and that's equal to m times the acceleration of the block in the x direction. In other words, I can cancel out my m's. We'll see that weight doesn't make any difference. Is what we need to do is have the x component of the acceleration of the block equal to g sine of theta. That's just what comes from Newton's second law. What we know, though, from the kinematics is that we're moving the cart with an acceleration along the horizontal, not along x. So what we have here for acceleration for the cart, I'll say, is going to be having a magnitude of a, and magnitude of a, let me draw this in. Let me see if I can get a blue line here for a. This is the acceleration we're going to give this thing. So the x component of that is, let me see here, let me get my angles correct. That's also a theta. So a cosine of theta in the x, so we got a sine theta in the j. So what we impart to this cart, if it doesn't slide, this is equal to ax for no sliding. If it does slide, it's also going to have a vertical component, and then that would be a different equation. So it says then, whenever I solve for this, basically says that a cosine theta, ax, must be equal to g sine theta. So the acceleration that we need to give that cart then is g times sine over cosine or tangent. So that's what we need. So again, the basic idea, draw the FBD. Some forces in X, I chose X to be along the guide there, and that gives the relationship between the X component of the acceleration and the weight, or the G sine of theta. And then recognizing we're pulling on it along the horizontal, we pull off the X component. If it doesn't slide, then AX is going to be equal to the X component of the acceleration of the cart. So that gives us the AG sine of theta.